So determine the open interval where the graph is concave up or concave down. So we get the first and second derivative to help us to identify the intervals. So solution. We start by getting the derivatives first and second, the function. So the first derivative is we're using quotient rule, x squared minus 4 times 2x minus x squared plus 1, 2x divided by x squared minus 4 squared. When you simplify this one, you get minus 10x over x squared minus 4 square. Second derivative, also using quotient rule, we'll have x squared minus 4 square times minus 10 minus 10x times 2 times x squared minus 4 times 2x divided by x squared minus 4 power 4. On simplification, the second derivative becomes 10 into 3x squared plus 4 divided by x squared minus 4 power 3. Now we discover from these two results that there are no points in which or at which second derivative of x equals to 0, but at x equals to plus or minus 2, the function f is not continuous. Not continuous. So we test for concavity in the intervals negative infinity to minus 2, minus 2 to 2, and 2 to infinity. So as usual, we draw the table. So draw the table. So we have interval. There are 3 of them. So negative infinity to negative 2, negative 2 to 2, 2 to infinity. And then we have test value. We have sign of the second derivative, and then conclusion. So from negative infinity to negative 2, we can actually pick a value like, say, negative 3. X equals to negative 3. So when we put negative 3, we get a positive value. So therefore, this is concave upward. And then in this one, we can pick a value like x equals to 0. So when you put into the second derivative, we get a negative value. So this is concave down. Here we can pick a value like x equals to 3. When you put into the second derivative, we get a positive value, so which shows that this is concave upward. So at the point x equals to -2, x equals to 2, which are not defined for the function, those are called asymptotes. So the lines x equals to -2 and x equals to 2 are the vertical asymptotes of the function. So therefore, with this, we can actually sketch the graph. So say this is -2, this is where we have 2. So this, we have vertical asymptotes. So because we have seen that now from -infinity to +infinity, then from -infinity to -2, the graph is concave up. So this is the shape of the graph. It's concave up. And then from 2 to +infinity is also concave up. So this will also be the trend. And then from -2 to 2 is concave down. Not touching 0. So this is the graph of f of x, all these three arms given by x plus 1 over x squared minus 4. So this is what we have. And then next example, determine the points of inflection. Determine the points of inflection. And discuss the concavity f of x equals to x power 4 minus 4x power 3. So solution, as usual, will start by getting the first and second derivatives. So f prime of x will be given by 4x power 3 minus 12x squared. Second derivative of this function will be given by 12x minus 24x. This can be factored as 12x into x minus 2. Now, remember that to get points of inflection, satisfy this equation. Second derivative equals to 0. So therefore we'll have 12x into x minus 2 equals to 0, which means that x equals to 0 and x equals to 2 are the points so really so you have now to get the corresponding values of y. So x and 2 are where the inflection points occur, i.e. the points of inflection will be 0, f of 0 and 2, f of 2. So you can just now find the actual value. So when x is 0, then the value of the function is 0, and when it is 2, so we'll have 2 power 4 minus 4 times 2 power 3. So minus 4 times 2 power 3. So minus 16. So these are the points of inflection. Please be careful. Don't say that x equals to 0 and x equals to 2 are the points. So remember, points would have x and y values. So that's why you have to calculate the values of the function at those points. So are the points of inflection. So then now we can always discuss the intervals for concavity. So we have from -infinity to 0, and then 0 to 2, and then we have 2 to infinity. So this is the interval. This is the test value. Sign of second derivative. Conclusion now. Conclusion. So this we can pick x to be -1, pick here x to be say 1, pick here x to be 3. When you put into the second derivative, then you get this value will be greater than 0. So this is concave upward. When you put 1, you get negative value. So concave downward. When you put 3, you get positive value, concave upward. So the sketch of this function. So with this information, this is how the sketch looks like. So 0, then we need 0.2. And then remember, when you put, you can also get the critical points. So critical points occur when you set, so critical points. So you set this equation 4x cubed minus 12x squared to 0. So we have 4x squared into x minus 3. So x equals to 0 and x equals to 3 are the values of x which give the critical values of the function. So therefore now at x equals to 0 and 3, so you can always test now from when you put 3 into the second derivative, from what to have seen, it is greater than 0, so it's concave up. So which means that then at this point we have this kind, and then at 0, when you put 0, we have concave down. So this is the situation. So we'll have so this is the point of reflection. So this is 0. So I have also point of reflection. So this is a concave upward. This concave, this limb here, concave downward. Then here we have concave up. So that's the sketch of that given graph. So as an exercise, not really an exercise, so the last example, find the relative extrema for the function f of x equals to 3x power 5 minus 5x power 3. So remember, we can get extrema by simply getting the critical points and testing their values. So f prime of x will be given by 15x power 4 minus 15x power 2. Then we equate this one to 0. So I have 15x squared into x squared minus 1 equals to 0. So x equals to 0, x equals to -1, x equals to 1 are the critical points. Critical numbers. So therefore now let's get the second derivative. So I'll have 60x of x power 2. So then now 60x squared. So remember the function here was, it's a negative sign here. So this was plus, this was negative. So we'll have plus, negative. So negative, so this will be plus. And then this will be negative. It's just okay, just okay. So the function was f of x equals to minus 3x power 5 plus 5x power 3. So the critical values will be, so f prime of x will be minus 15 x power 4 plus 15 x power 2. And then let's get the second derivative. This will be given by minus 60 x power 3 plus 30 x. So critical points, critical numbers will be setting minus 15 x power 4 plus 15 x squared to 0, which is the same thing as minus 15 x squared into x squared minus 1 equals to 0, so that x equals to 0 and x equals to plus or minus 1. So the critical numbers are x equals to 0, x equals to negative 1, and x equals to 1. Now we can test for the relative maximum or relative minimum using putting the critical points into the second derivative. So using second derivative of x, which is the same as minus 60 x power 3 plus 30 x, which is 30, into minus 2x cubed plus x, we use second derivative test to find relative extrema. So points can write in form of a table: points, sign of the second derivative, and then conclusion. So we have when x is negative 1, y will be negative 2. And then when x is 1, and then when x is 0, y is also 0. So sign of the second derivative at negative 1 is positive. So this means relative minimum. And then second derivative at 1 is less than 0, so means relative maximum. And then at 0, so test fails. So second derivative test fails, but using the first derivative, test 0, 0 is a point of inflection. Since from the first derivative you can actually test. So if you say this 0, then pick a value like negative 0.5, 0.5. So when you put into the derivative negative 0.5, so we'll have 15 answer square into 1 minus answer square. Have positive, and then 0.5. So 15 answer square into 1 minus answer square, still positive. So therefore, the point 0, 0 is neither a relative maximum nor a relative minimum. So that's the end of that question.